We're still trying to answer this question, how to build a working circuit at the lowest possible cost. And we know how to get an answer by applying Boolean algebra and then massaging the equations. But let's look at a new technique, a more visual one, which is the Carnot mapping. And the motivation again is, if I look at this truth table with 4 inputs and I try to take the sum of products equation, I'm looking at the ones on this truth table, I get something like this. And now the way that I have to simplify, at least until now, is to find the common terms and start putting things together and canceling gates until you get something that gives you your minimal cost. But can we find a way that it's a little bit more robust to error, to mistakes, and we can visualize how to simplify these in a faster way? Well, the answer relies on your KMaps. So the more inputs the logic circuit has, the more complex the Boolean expressions become. So KMap is a visual method for spotting terms that are similar. So it's a more manageable approach. It provides also a systematic way of producing a minimum cost logic expression. And the key to the Carnot mapping approach is that it allows the application of two properties, which are these ones, 14a and 14b, from the book that I'm providing on Canvas, the chapter that I'm providing on Canvas. And you're pretty much applying Boolean expressions, these two properties of Boolean expressions, of Boolean algebra, but in a visual way. So let's look at the two variable min terms. Let's say that I have a table with 2 inputs. I just have random outputs right now, just to give an example. And I ask that I want to get the minimum cost for this truth table. So I put the rows over here, so 0, 1, 2, and 3, so the minimum terms. And KMap wise, you're going to have 4 combinations, and you're going to write the most significant bit on the top and the least significant bit on the bottom. And then here is going to be when the most significant bit is 0, and here it's 1, and the same thing for your least significant bit. And now over here, you're going to put your minimum terms. So here goes minimum term 0, 1, 2, and 3. So notice here, minimum term 0 is when my most significant bit is 0 and my least significant bit is 0. That's correct. So if I put the values, I get a 1, 1, 0, 0. All right. There is another way of doing this, and just a heads up, sometimes you have some books or professors that they like to swap the least significant bit with the most significant bit, and they put it on the top the least and on the bottom the most. It's exactly the same thing, but now the minimum terms are organized slightly different. Instead of having the 1 on the bottom left, now it's on the top right. You just apply exactly the same thing and it works all the same. The way that I'm going to use for Intro to Mechatronics Systems 2, or this quarter, is the one on the top, where the most significant bit is on the top. So let's go back to our KMap, and now how do I take the expression out of the minimum circuit out of this KMap? So what you're going to do is, you're going to look for pairs, horizontal or vertical, but never diagonal. Alright, pairs of ones. So if I look at here, I have a pair over here. That's my only pair. And now how do I take the expression out of that? So notice that you're going to find what is common to this pair of ones. And the only thing that is common is the 0 over here, when your A, your input A, is 0. So notice that this group of ones belongs to 0 and 1. So I cannot write this expression in terms of the least significant bit. So that becomes A negated. And that's your simple equation. Groups of 4 are also important. So you're going to do powers of 2. Obviously here you can only do groups of 2 or groups of 4. If it's a group of 4, if you have all ones, is going to be your F is going to be equal to 1. So if I have 1, 1, 1, 1 on my KMap, your F is going to be equal to 1 because it's a big group of ones. All right. Let's exercise here, stop the video and try to find the canonical expression without simplifying, and then find the minimal cost. You can do it by hand and then applying KMap. and then continue the video to see the solutions. Alright, so canonical form, I have the circuit over there, but if I take the expression, I can go here and say that f is equal to x1, x2 negated plus, so this is this term over here. Now our second term is going to be when x1 is negated and x2 is positive, and I have one more term, which is when x1 and x2 are both, which is the last term over here, are both 1. So I have 3 minimum terms. It's no surprise that I have 3 AND gates. They all connect to your OR. And now if I simplify these by using a Boolean, if I massage Boolean expression, if I massage this equation, I find two common terms, one common term between these two terms, which is x1 negated. And I can also find, I can reuse terms in Boolean algebra, and I can also find these two over here, which gives me x2 and x1 or x1. Now notice that this is the same thing as having 1. This is the same thing as having 1. So I get x1 negated or x2 by massaging my Boolean expression. And notice that you're already seeing the solution here by looking at the KMap, that instead of doing all these, I can just find the groups of ones. And remember that I'm reusing terms over here. This is the same thing as reusing the ones for the pairs of 1. So if I go and I put x1 and x2, x1 is my most significant bit, x2 is my least significant bit. Let's see if I can erase, sorry, let's see if I can erase this part over here. We have some space. All right, and so this is your most significant bit and this is your least significant bit, and I put the 1 over there, that 1 goes there, that 0 goes there, and that 1 goes over there. If I group these together, the common term is x1 negated, and that's what we have over here. And if I group these two together, I get this one, x2. It's the only one that is common to this, so you get your x2. So here you go. This is how you take an expression out of a KMap for 2 terms. Now, if you have 3 variable mean terms, you apply exactly the same concept, but let's see how do we build our KMap. So you write your minimum terms, and in this case the KMap is organized as the following. You're going to put the 2 most significant bits on the top, so AB goes on the top and C on the bottom, and here are just the combinations for 2 bits, which is 4 combinations. But be careful here, this is called the gray code, and what you do is like you have 0 0 0 1, and a lot of the time students forget that this is gray code and they just write the 1 0 here, but you write 1 1 and then the 1 0. This is just to guarantee that you only have 1 bit changing as I go from one point to the other. So notice 0 0 0 1, only 1 bit changes, 0 1 to 1 1, only 1 bit changes, and the same thing when I go here. This is called the gray code. If you don't do that gray code, then it messes up on getting the minimal cost out of the KMap. Your C is simple, it's just 1 bit, so 0 and 1, and now you put the respective min terms in this placement, in these places. Alright, so this is what you get, and now we're going to start grouping, and you see that you have 2 possible groups here. So we're going to look for pairs, horizontal or vertical, but never diagonal. So I get the group over there and a group over there. And if I took the expression, so notice that for this pair of ones, it's when A and B are 0. And for this pair of ones is when A and B is 1. And here you go, it's simplified. You can do groups of 4, and because now you have 3 terms, you can go also do groups of 8. So if you have ones over here, you can group those 4 together, so forth and so on. We're going to see a couple of examples next. Alright, so pause the video and try your best to find the canonical SOP and the minimal cost by the 2 methods, by massaging your Boolean expression out of the canonical, and then apply the KMap and see if you can get the same answer. So what do we have as the canonical form. So notice here that I have 1, 2, 3, 4 minimum terms, and that's why I have 1, 2, 3, and 4 minimum terms. And I could massage these and find the common terms, but I'm going to let you guys practice that. And I'm just going to design the KMap. So I put the two most significant bits, x1 and x2, and the least significant bit over here, x3. I do the gray code 0, 0, 0, 1, 1, 1, and 1, 0, and then I put these values inside of my KMap. And now I'm going to group ones. So remember, I cannot group diagonal, but the cool part is that I can actually group this one with another group, with another one from the other side. So this is a valid move on KMaps. So if I group these two together, what do they have in common? So if I look at here, they're going to have in common the 1 of x1, right? Because x2 is changing, so it's not common. And also x3. So that's why you get x1 and x3 negated. And what is it common over here? So we're going to have x3 because it belongs to x3. And if I look up, it's when x2 is negated because I have zeros on the group of this group of ones. And here you go. This is your minimum expression. Let's go over another exercise. Same thing, 3 terms, stop the video, get the canonical SOP and the minimal cost by using KMap. Alright, so I have 1, 2, 3, 4, 5 min terms. 1, 2, 3, 4, 5 min terms. So it becomes a little bit tricky to find the minimal cost. So let's do the KMap, x1, x2, x3, and I put all these variables over here. And now notice again, I can do powers of 2, so I can group 2s, 4s, and 8s, and I can also have one single ones. It's totally fine to leave one just by itself. So here I can, and I always want to maximize the grouping because that gives me a smaller expression. I'm finding the most common terms between those ones. So that these ones, these 4, all what they have in common, it's only x3 negated because all these bits are changing, so only this is the one that it's common. So here you go, x3 not. On these two ones, what I have in common is the 1 and the 0. So x1 and x2 negated. And here you go. Just by looking at the KMap, you find the expression super fast. Now notice here that why do we want to maximize the number of grouping here, the number of ones when we do groups? Imagine that I don't do this grouping over here. And imagine that I leave this one alone. And I just put these 4 ones together. So x3 will be part of my answer, but now that one is going to be x1, x2 negated, and x3. Notice that here I'm going to use more gates because I have more terms than over here. That's why the importance that if you can group ones, you group them. You don't leave them alone. You only leave them alone if you don't have any other option. Now let's go over the 4 variable mean terms, and we stop here for Intro to Mechatronic Systems 2. So for the 4 variables, I have 16 combinations. So here is just showing from 0 to 7, but you should have from 0 to 15. And the KMap is the following. What you're going to do is to write the most significant bit A and B on the top and the least significant bit on the bottom, C, D. You're going to write the gray code on the top and now also the gray code on the left. And now you place the minimum terms on your table. Again, you don't need to memorize this placement. You just need to know how to read this table. So if you know how to place the gray code, now you just need to know that this 1 goes where you have 0, 0, 0, 0. So 0, 0, 0, 0, and it goes here. And you kind of place, but there is a way of filling these fast when you start getting more practice, which is you put 0, 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15. So again, the more you practice, the easier it will be to fill these tables, but for now, if you have the gray codes, you're good to go. And now This blue part that you see over here is going to be what's common on these positions that are covered by these blue arrows over here. So as an example, if I have any grouping of ones that I do that are under these two columns over here, I know that A is common to those ones. That's why you have this position over here. If I have the one over here on the other end, then I know it's going to be A naught because it's outside of this blue arrow. The same thing applies for all the other letters that you have over here. They're just indicating you either the columns or the rows where the ones, if you do groups there, they have these inputs as common terms. So let's practice. Before we practice, let's just give some examples. So now you can group 2, 4, 8, and 16. Remember, never diagonal, but this third option over here, which is pretty cool, you can actually group the corners of your KMap. So if you have ones, 4 ones, so one on each corner, you can actually put them all together. And here is just giving examples. So I can group these ones with these ones, 2 together, 4 together, 8 together. I can do a 4, 4, and I can do 4 on the bottom here. So here, a common mistake that students do is like they group 4 and then they just group 2. Remember, the more ones you include, powers of 2, the less terms you have, the simpler your equation is. And it's fine, you can reuse terms and you get something like this. So let's practice. Let's put here an example. I'm going to just give the KMap right away. I'm going to design a KMap here. And I'm going to put random ones on this KMap, and then I want you guys to stop the video and try to group before you see the solution. So I'm putting the gray code, the most significant bit and the least significant bit. So most on the top and least significant bit on the bottom. Just putting random ones right now with no particular order. And the rest are zeros. All right, and I want to take now my SUP. So let's do the grouping. Let me change the color here and let's group the ones. So I have these two ones can be grouped together. I have these two ones can be grouped together. These two ones can be grouped together. And now I have these two ones. And now I have this one over here that I have two possible options. You either group this one with the one on the corner or you group this one with the one on the bottom. You just pick one. I'm going to pick this one. So as you can see, there are multiple answers that you can get. All right, so now let's take our solution here. So let's start with these two ones over here. So notice what it's common between them is C and D negated. So C and D negated. Let's just do the tables on the top. So let me see here. Let me put my A, B, C, and D. This is my help here. So if I go to my 1, 1, so notice that this 1, 1 is outside of A, so it's going to also have the A naught, is outside of my C, so it's C naught, and is outside of the D, so D naught, but it does not include B because the group of ones intersects the B and the B naught, so B is excluded. So now let's go over this one over here. So if I look at that one, I know that it's on the A naught and it's on the B naught, right? These two, and it's on the C naught but not D. So C naught, but D is not included because it intersects D. Notice that I'm getting three terms here on this minimum term because I'm just grouping two ones. So now let's go and do the middle one. So the middle one does not have an A, it has the B, the C, and the D. So what you get is B, C, and D. All right, so now let's go over this one on the corner here. So it's going to be your A, your C, and D naught. And at last, this one over here with this one over here, it's going to be your A, B naught, and D naught. This is one solution. If you group this one with this one over here, your last term is going to be different. So when you are in the Boolean expression, if I was taking the canonical, that means that you find a different term, a different common term when you are grouping the terms together, which is totally fine. Both answers are correct. And one more thing, as we are taking the SOP, taking the ones, but you can also take the pause. And how does it work with the pause? So for the pause, let me just change here the color. For your pause, now what you're going to do is you're going to look at or group the zeros and take the expression. So if I go here and I group the zeros, it works exactly the same thing. Pairs or 2, 4s, 8 or 16 in this case. So let's go here. So I have 2 zeros over here. And I have 2 zeros over here. I can group these 2 zeros together, these 2 zeros together, and these 2 zeros together. Perfect. Now let's take our expression. Same thing applies here as you're taking to the truth table. You can either write your SOP and negating your F negated and then apply De Morgan's to get your pause, or you can take directly the pause. Let's do the first one, taking the SOP and negating F. So now if I go here, this first zero as A, B, and C naught. So A, B, and C naught. This one over here as B, C naught, and D. B, C naught, and D. This one as A, B naught, and D. A, B naught, and D. This one is A naught, B naught, and C. A naught, B naught, and C. And this one is A naught, C, and D naught. A naught, C, and D naught. Here you go. This is not done yet. Like if you take it like these, now you need to apply De Morgan's by applying these negation on top of all of them. But what we can do is we can apply De Morgan's directly. I know that I can just invert my variables over here and make an OR and then an AND between them. So actually my F, my pause is going to be A negated or B negated or C, B negated or C or D negated, A negated or B or D negated, A or B or C negated, and A or C negated or D. And here you go. That's your minimum circuit for your pause. Now, which one are you going to build? This one or that one? Well, sometimes SOP is easier to build than the pause and vice versa. So you always need to take the SOP and the pause out of the KMap and see which one has the minimal cost, and that's going to be the circuit that you're going to build.